In this video, we're going to walk through a number of parallel ways to simulate differential equations, and in particular leading towards a control aspect where we get to add our own control on top of an existing dynamic system. We're going to start with our 3D printer hot end, which is basically a replacement for Newton's law of heating and cooling. So we have our differential equation, and what we're going to see is three different representations of that in Python and how they get implemented and any technical details along the way that we need to be aware of. In terms of modules that we need, the first two modules we've used frequently before. There are two new modules that we have not used previously, and they're SciPy Integrate. We're going to need the ODE integrator. I believe you've used that earlier in the Mech 202-203 sequence. And we're also going to use the signal tool out of the SciPy library as well. We're going to see how that gets used for state space models, as well as the transfer function Laplace models. To make sure that we don't bury our constants too far down the rabbit hole here, what we're going to do is look at our model right at the outset, and we're going to define our value for k initially, and we're also going to define our b and u's. Well, actually, we're going to use b and u as 0 for this particular instance. We're going to start off simple. And anything else that we need to define for the simulation. So we're going to simulate for 20 seconds. And the idea here is that when we get a graph, we're going to see 0 to 20 on the x-axis. And we're going to have our initial temperature here of 5. From this model, what we'd expect is if the control is off, then we should just get an exponential decay of our temperature down towards 0. So x is our temperature, and it'll decay downwards. So our first model is based on the ODE int solver. And what we need for that is we need to define a function, and I usually call it something like our differential equation, like this, or DE model. And it's a function of x and t. So that order is important. It has to be x and t unless you do some other overrides, or y of t is what you'll often see in the documentation as well. The key thing is it's your state value and then the time next. And the idea behind this is we just build our dx dt. And it's going to equal, straight from the paper version here, minus k times x. And we're not going to leave a control in here, so we'll have that as plus 0. So we're going to leave the plus bu off for this round. And then we just return that, actually, dx dt. I'm going to put a little more detail in this one than I usually might. We could have just returned this, but we're going to see more complicated instances where it makes sense to do piecewise calculations and return one thing at the end. All right, so that's our basic model. So the next thing we need to do is build our simulation. So we'll start off with just a t value here, and these are going to be linearly spaced between 0 and we have it up here, simulation time. So we're going to sample that, and by default that'll be 100 points between those start and end points. So if we do this and we just print our t value here for a second, we're going to see an error, of course, and that's because I didn't run these first 3 lines. There we go. So we're going to get 0 as our first time value all the way up to 20, and there's going to be 100 points spaced evenly in between those. Now the lovely thing about this method is it's actually really simple. What we can do is now solve our differential equation, and it's just ODE int. We've already imported that whole thing. We don't need a preface, and we just put our DE model. And what else do we need? We need our starting condition and our time values. And if there are any questions, what I do is do ODE int here, and the ODE int function takes in your model, the initial value, x, y, and t, and then a whole bunch of other possible options, but we're happy with the bare bones model for now. So let's run that, and we'll print x just to see what happens. Okay, so x is one big long column vector, and notice it starts at 5 and then goes down from there, which is exactly what we expect if we have something cooling off from temperature 5. It's much easier to see that if we plot the results, though, of course. So let's do a PLT plot of t on the x-axis, on the horizontal axis, and then x as the temperature on the y-axis. And we'll add some labels on there. 100 seconds, and we'll add our y label as temperature in degrees Celsius. All right, then we got our nice plot. So what we've been able to do here is start off with a natural expression of a physics system build the model, translate the model into Python, and simulate it. Now, that's one way to do it. It's important to note, of course, that what we get is actually a set of points. We don't actually have a graph. We don't have a function, but we do have, let me get this right, here we go. We get a bunch of points back. And these are the x values that we see here. So x is a vector of numbers, time, t is a vector of numbers that corresponds to those x's and vice versa. So we can infer some things like how long it would take to cool down to a certain temperature, but we don't have a formula explicitly that we can work with. That's okay in many situations. What we're going to do now is repeat that calculation, only this time we're going to use the state space model. And just remembering the state space model has the ingredient of the x's, so we're going to treat that as our temperatures. And it has this observable y thing, which for us right now, we're just going to basically ignore, except we can't leave it out because the computational stuff all assumes that there is a y value in there somewhere. So what we're going to do is just make it 1 times x and 0 times u here. So basically we're going to turn this into y equals x for the purposes of our calculation. Now how does this work? Well, take a look at our math here. When we translate this equation right now into a state space model, that's easy because it is a first order equation just with only one variable. And so our A matrix is just going to be the coefficient of x. Well, that's just minus k. Our B is going to be 0, so we're not even going to include that, or we'll include it as a 0 value. And then, as I said here, we're going to have our y equals x as our observable side. And so we're just going to make that C matrix 1, and D is going to be 0. So we just make them. NP array with a value of minus k. B is an array with values of 0. C is an array of 1. And D is an N of P array with a value of 0 as well. So nothing fancy happening here. What we're doing again is just taking an alternate translation of the math on paper into the expressions for our Python code. All right, what else can we do? Well, with that, we're going to introduce some new technology here. And this is going to be used in the signal array. So what I'm going to do is do signal.statespace. Take a look at that. And what we're doing is a state space model, so thus the state space thing here. And what this does is actually creates essentially like the function we had before, where we called it DE model, except it just has different syntax. So what we can do is pass in the arrays A, B, C, and D, and that'll create a system that we can use. So let's try that. We're going to call our state system equal to system. Is equal to the signal library state space. And then we literally just say, well, it's defined by A, B, C, and D. If I know those, I know my entire system. And if you look at the math on paper, we know the entire system because we have those 4 matrices. So we are good to go. That doesn't define what we start at, though, or it doesn't actually do any simulation. So we're going to do that next. Actually do the simulation. And here, what we're going to use is the lsim command. So again, looking up in the help, or I can look and Google it. So here we have to put in, just like our model before, we put in our system that we just created. We have to give it a control value, a list of time values, initial conditions, and interpolation. We won't do that, but we do want an initial x. So system u, t, and x naught. Here, though, we don't actually want a u value. So what we're going to do is set up, we're going to set time values for our states. Same thing as before, 0 to our simulation end, simulation time here. So we'll get a graph from 0 to 20. I'm just going to change this up a little bit, not for any particular deep reason, but just so the graphs don't overlap each other. I want to be able to compare all these graphs together, and what this will do is use 150 time points. So it'll be a little bit different than when we used 100 time points here. So not required for the simulation, just a nice way to be able to separate the graphs later on when we compare them. And the nice thing about the U state is that we don't actually, let's actually call it U, it's the control. And we want this to be all zeros. So this is going to be NP zeros, and it's the length of T state. Let's see if that works. Seems to run, okay. And that was pretty much it. We're now ready to run it with signal.lsim. So signal, I'm not sure what the L stands for, but simulate basically the state system that we had. And our x naught is going to be an array of just 5.0. So this is our initial x value, our initial temperature. Our u is going to equal our little u here, and our t is equal to our t state. We're going to try that. That ran successfully. Excellent. Notice we get a whole bunch of things back. We actually get 3 things back. It turns out what we get back is the time values again, for reasons that are lost on me, but there they are. And the x state and the y state. If we go back to the model that we're looking at with the state space, having the x's and the y's as 2 separate components, it makes sense that we're getting information about both separately. So if we do this and run it, what we now have are the t state and the x state variables. So let's try this out with a plot. In fact, we can now let's do it from scratch. Plot the results. So what that line did here was it did essentially the same thing as the ODE integrator, only it used a different representation for our system to say, well, how do I go one step further in time, update your rates of change and so on. But everything about the plotting is going to look very similar. We're going to plot t state against x state, the 2 values that we got back here. Let's just try that first. Perfect. And let's put those as dots just to remind ourselves that yes, they are dots. So this has all the time values we had from 0 to 20, and we're just going to borrow that so we get a nice axis labels on our plot. And of course, this looks very similar. In fact, it should be identical because we're just representing the same system in a different way and using a different simulator. If all the simulators are roughly equivalent in accuracy, we should be getting the same basic result. All right, last but not least, now Laplace transforms and transfer functions are the least familiar for most of you, so walk through this in a little more detail. The differential equation is here again, and what we do is we take the Laplace transform of both sides. We do that crazy exponential. In practice, we just look things up in a table, and so what we get is the Laplace transform of the derivative of x is going to equal the Laplace transform of the right-hand side. Fair enough. Now, the idea is we don't know what x is, and we don't know what u is, but we can take their transform in principle, so we get these capital letter u's and capital letter x's. And the derivative, when we take a Laplace of it, basically ends up with s times the original function itself. So we get that as a nice property of the Laplace transform. And there's also something to do with the initial conditions. So basically, we get initial condition stuff showing up here. We bring it to the other side. And what we end up with are 2 x's in our equation here, one from the right-hand side, one from the left. They move them all to the left. And we end up with s plus k as a common multiplier. And so we get this 1 over s plus k here times stuff to do with the initial conditions. Whoops. Times stuff to do with the initial conditions. And stuff to do with the control. We're going to delve deeper into the mathematical significance of that, but for now it's enough to know that we can represent this cooling system by this 1 over s plus k term. That's our g of s. That is our transfer function that somehow captures what this thing does, what this cooling system does when we apply initial conditions and a control to it. So the syntax for this is we look up signal, and then we look up transfer function. And we see it's a system, there's a bunch of arguments, blah, blah, blah. The key thing here is we're using this version. We're basically going to give the numerator and the denominator to this function and say, I have 1 over x plus k. Well, I just need the numerator. And actually, let's bring that back for 1 second. I think it's helpful to see the expression because they actually have an example in here. So what they wanted in this function was, say, s squared plus 3s plus 3. The way you input that into Python, there has to be a system. We're not just going to type that in, unfortunately. But we just rhyme off the coefficients from the highest degree down to the lowest. So their numerator is represented by 1, 3, 3, because the coefficients are 1 for s squared, 3 for s, 3 for the constant. And then for the denominator, it's the similar argument. We start at the first coefficient, the highest power. That's a 1, then it's 2s, and then it's a 1. So 1, 2, 1 is the denominator. So in fact, this is in some ways the easiest to represent for us because we just do numerator is equal to literally 1, and the denominator is equal to literally, oops, that should be an S, I apologize. It should be S plus K, so it's 1 and a K. And that's it. And let's make these arrays just to make it fancy. Same as we did before. Just nice to have some consistency here. Comma K. So literally, we can capture this entire system with this transfer function. That's at least the claim. So how does that work? Well, we do the same thing we did before. We're going to do a transfer system, and it's going to be defined by a signal built out of a transfer function. And all we have to give it is the numerator and the denominator. And that's it. Nothing exciting happens, again, because we have to do the simulation. But the nice thing about this signal system is that we can just grab all of this, I think. We'll take a close look at it again before we use it, but we're going to build our T's, and let's make sure we replace all these. This will be T for the transfer, and we're going to replace that everywhere. There we go. And we're also going to get X transfer and Y transfer. Let's call that Y transfer. And the system that we're using is the transfer system. There we go. So I think we've gotten rid of all of the states and replaced them. Oh, there's one more state. Nice transfer. There we go. So the nice thing here is that the simulation works exactly the same way. We just give it a different embodiment of the system. We've got it in a different way, and we just use it instead. And let's go 225 or something here. Perfect. So we're getting a nice graph, exactly the same kind of structure we got before, only with more points. And it makes sense at this point, honestly, to just plot all three of those in different colors so we can get the comparison between the three of them and see, for the same system represented three different ways, are we getting the same thing? So we had T state and X state. And let's make this a big figure. So we're going to do a PLT figure. Fig size 15 by 15. Make it nice and large. And then what do we do? Got these. Let's make it red, black, and green. Let's see how that works. Fantastic. Okay. So what we can see here is that, in fact, yes, all these graphs are essentially the same. If we take out the dots, again, represented, noting that we're representing our functions, not as functions, but as just a sequence of points that we predicted, they're on top of each other. These would be indistinguishable for most purposes, especially at the resolution of a cooling fin or a hot end in a 3D printer. But you can see that they actually are different in the sense that they were generated three different ways. The green dots were the most recent ones. We have more of them. The black dots and the red dots are more spaced out because we used fewer points for those. So that has given us three different ways to represent a system, and not just three different ways to represent it, but ways to simulate it based on those representations. Now, a natural question is, well, if they're all the same, why do we need three different ways to do it? The reason is sometimes it's easier to come up with one of the models, and so you want to use that. The reason to have at least two of them in at play at any time is because you want to be able to compare and just make sure you haven't made a mistake in implementing one or the other. Here we have a perfect match between the solutions, which says, yes, when I represented this in my code and on paper, that whole translation process led me to the same n both times, or all three times, so I'm very confident that what I'm doing here is correct. So that gives us a good starting point for working with these kinds of simulations.